Hello my precious friends, I really hope that you are doing great. Welcome to our today's class. It is our second lesson on the second topic of Form 4, which is called Uniform Circular Motion. As usual, let me commence by giving the quote of the day, which states that good decisions come from experience. Therefore, don't be afraid of experiencing the ups and downs of life. We shall discuss that quote at the end of our class today. So today we're looking at the centripetal acceleration. So we are saying that a body moving around a circular path is accelerating though the speed remains constant. So this because the velocity keeps changing with position, whose direction is always directed along the tangent. That is, as you can see. So you can see this particular body, the velocity of the body is always moving along the tangent. Remember, a tangent and the radius of the body will always meet at an angle of 90 degrees. So we are saying that the speed of the body is remaining constant though the body is accelerating. Remember, acceleration is change in velocity over change in time. So consider if the body is moving from point A to point B to point C and back to point A, actually because this particular body is moving along a circular path, it means that the direction of motion of this particular body is actually changing with time. For instance, consider the body at point A and when it is at point C. If the body is moving at point A upward, actually, the motion, that is the velocity, is directed upward. So if we take the upward direction to be positive and the downward direction to be negative, if the body is moving at a uniform speed of 20 meters per second, it simply means that the velocity of the body at point A will actually be positive 20 meters per second. The reason being, velocity is a vector quantity, therefore we must look at both the magnitude and its direction. So if we take the upward direction to be positive, then the velocity of the body will be positive 20 meters per second. However, if the body moves up to point C, at point C you can see the body is moving downwards, therefore its velocity at point C will actually be negative, because if you are taking the upward direction to be positive, then the downward direction must be negative. So because the body is moving at a uniform speed of 20 meters per second, then its velocity at point C will be negative 20 meters per second. So negative to show that it is moving in the negative or in the downward direction. So you can see that the initial velocity is 20 meters per second, then the velocity at point C is negative 20 meters per second. Therefore you can see that the velocity here is negative 20, the velocity at point A is positive 20. Therefore the velocity is actually changing with time. In Form 3 under linear motion, you can just check it. It is the first chapter that we covered in Form 3, that is linear motion. We did define acceleration as the change in velocity divided by time. Therefore, whenever velocity is changing, for example, in this case, it is changing from the positive to the negative value, then such a body must be accelerating. So because the velocity is changing, that particular body is accelerating. But we are saying that the speed is uniform. Why? Remember, speed is a scalar quantity. Therefore, because speed is distance over time, and both time and distance are simply scalar quantities, therefore we don't look at the aspect of direction. Therefore, the speed of the body at point A is 20 meters per second. The speed of the body at point B and also at point C is still 20 meters per second. So for the speed, we don't check the direction. The reason being, speed is a scalar quantity. But therefore the speed is actually constant at point A, at point B, at point C. So the speed remains uniform, or it is constant at all points. That is from point A, point B, point C, and even back to point A. However, the velocity is changing because of the changing direction. So at this point, the velocity is positive 20. When it goes to point C, the velocity is negative 20. Because there is a change in velocity, and remember, change in velocity over time, that is acceleration. So whenever velocity is changing, such a body is said to be accelerating. But because the speed remains constant, so we don't look at the upward and the downward direction for the case of the speed, because we said that speed is a scalar quantity. So the speed remains constant, but the velocity of the body is changing, and hence the body is accelerating. So it is possible for a body to be accelerating when its speed is constant. A good example is when a body is rotating in a circular path along a fixed point O. So of course this is the radius of the path. So according to Newton's second law of motion, a resultant force must be acting on the body to produce an acceleration. So this resultant force that produces an acceleration on a body moving around a circular path is what we call the centripetal force. Remember, centripetal force is simply a force that tries to constrain a body to move in a circular path. Again, we discussed about centripetal forces in Form 1 under a topic called force. Again, we covered it in this particular channel. You can just refer from our Form 1 topics. We actually defined centripetal force. A good example of centripetal force in real life situation is the merry-go-round. So this force is called centripetal force and is always directed towards the center of the circle, such as the one shown in this particular diagram. So this force is also called the center-seeking force because it always acts towards the center of this particular body, for example, at this particular center. Then the acceleration produced by centripetal force, we call it the centripetal acceleration, and it is given by the formula acceleration is equals to v squared over r. So from Newton's second law of motion, which stated that force is equals to ma, remember we looked at Newton's second law of motion when we were looking at the Newton's laws of motion. Again, that is a topic that we covered in this particular channel, so you can just refer Newton's laws of motion. We stated the Newton's second law of motion, which simply stated that the rate of change of momentum of a body is directly proportional to the resultant external force producing the change and takes place in the direction of that particular force. So from Newton's second law, we showed that force can be given by ma, where m is the mass of the body, a is the acceleration of the body. So if I substitute the value of centripetal acceleration, which is acceleration is equals to v squared over r, where v of course is the linear velocity, so v squared over r. So this formula will simply become, where I have a, I'll substitute with v squared over r, therefore force will be equal to mv squared over r, where the force is the centripetal force and of course a is the centripetal acceleration. Therefore centripetal force can be given by the formula mass times velocity squared over r. Similarly, from our previous class, that is Uniform Circular Motion Lesson 1, we did derive this formula. We said that linear velocity can be given by radius times the angular velocity, or simply the omega. So if I substitute v is equals to r omega, in the formula force is equals to mv squared over r, I'll simply have, where I have v, I substitute with r omega, so this will be r omega, but because it was v squared, so this will be r omega squared. If I open this bracket, I'll have mass multiplied by r squared omega squared over r. So of course r squared divided by r, I'll just remain with 1r. Therefore the centripetal force can be given by mr omega squared, therefore which is just m omega squared r on rearranging. Therefore the centripetal force can as well be given by mass times the square of the angular velocity times the radius. So if we plot a graph of force in Newton against omega squared in radians squared per second squared, we expect a straight line graph to be obtained. So if I analyze this particular graph, I'll simply rearrange this particular equation in the form of the equation of a straight line graph, because this is a straight line graph. So if I rearrange this equation, I want to take r to pre-multiply omega squared. So on rearranging this formula, I'll simply get f is equals to mr multiplied by omega squared. So I'm rearranging so that it aligns with the equation of a straight line graph, which is y is equals mx plus c. So you can see my y-axis is having the force. You can see similarly my y-axis is having the force. Then the x-axis is having the square of omega. You can see my x is rhyming with omega squared. Then of course plus c. So the value of c, because this one doesn't have a plus c, so it means the value of c is 0, and that is why the y-intercept or the f-intercept is 0. You can see that our graph is starting from the point 0, 0. So you can clearly see that m, which represents the gradient, will be equal to the product of mass times the radius. So the gradient or the slope will always give you the mass times the radius of that particular circle that is being traced. Therefore, maybe you can be given a graph. They can tell you to plot a graph. You can be given values to plot a certain graph. Then they'll ask you, you'll be given maybe the mass of the body. Then they'll ask you to use the graph to find the radius. So you simply calculate the gradient or the slope of that particular graph. Then the value that you obtain, you equate it to mass times the radius. So if you are given the value of mass, you can easily compute the value of the radius. So similarly, you can that is from the same formula. We have said that v is equals to r omega. So again, you can also be plotted a graph of v squared against r. Of course, v squared in meters squared per second squared against the radius r in meters. So the graph of v squared against r, so you simply play around with this particular equation. so that it aligns with the equation of a straight line graph, because you can see our graph is a straight line graph. So I'll start by multiplying both sides of this equation by r. So I'll have fr being equal to mv squared. So fr is equals mv squared. Then I'll divide both sides by mass so that I make v squared subject of the formula, because you can see my y-axis is having v squared. So over m, I'll simply obtain v squared being equal to f over m multiplied by r. So you can see this one is rhyming with the equation of a straight line graph. So you can see v squared is on the y-axis, so v squared is rhyming with my value of y. Then the x-axis, we are having r, so you can see my x is also rhyming with r. So when they are rhyming, the value of m will represent the gradient of that particular graph. So you can clearly see that m, or the gradient, will be equivalent to force over the mass. Therefore the gradient will give you force over mass, and from force is equals to ma, if we make a subject of the formula, that is by dividing both sides by m, then acceleration will be force over m. Therefore the gradient or the slope will give you f over mass, which is equals to the acceleration of the body. So given values, you can use this particular graph to find the acceleration by simply equating the gradient to the acceleration, or equating the gradient to force over mass. Next, we look at the factors affecting centripetal force. So we'll base those factors on the formula for the centripetal force, which was F is equals to the mass times the square of the angular velocity multiplied by the radius. So the first factor is the mass of the object, whereby you are seeing that the centripetal force will always be directly proportional to the mass of the object from this particular formula. That is, if we hold the square of angular velocity and the radius constant. So a heavier object always requires a large centripetal force to keep it moving in the circular path. So consider this particular stone, which is being rotated by this particular string about this particular point O. So if the stone is being rotated in this particular direction, so obviously if you use a much heavier stone, you would require a very large force in order for you to maintain it rotating in that particular circular path. And of course, if the stone has a very small mass, you'll just need a very small force within your hand in order to whirl or to rotate this particular object in the circular path. Therefore, the resultant force required will always be directly proportional to the mass of the object being rotated. So a heavier object requires a large centripetal force to keep it moving in the circular path. Conversely, that is, a light object requires a very small amount of centripetal force in order to keep it moving in a circular path. Therefore, the mass of the object is directly proportional to the centripetal force required. The second factor is simply the angular velocity of the object. So from this formula, you can see that centripetal force and the square of the angular velocity are simply directly to one another. If force is directly proportional to the square of angular velocity, that simply means that force is also directly proportional to the angular velocity. Therefore, increasing the rate of whirling, to whirl is simply to rotate the object in a circular path, such as this one shown here. So increasing the rate of whirling requires a higher centripetal force. So the rate of whirling in this case corresponds to the angular velocity of the object. So the faster the speed with which you whirl that particular object, the larger the angular velocity. Therefore, increasing the rate of whirling requires a higher centripetal force. So in order for you to rotate or to whirl this particular stone in the circular path at the highest speed possible, you need a very large centripetal force within your hand in order for that particular stone to rotate at the highest speed possible. Therefore, the centripetal force is directly proportional to the angular velocity, such that increasing the rate of whirling requires a higher centripetal force, or increasing the angular velocity requires a very large centripetal force within your hands. Then the third and the last factor is the radius of the path. So the radius of the path simply corresponds to the length of the string or the length of the rope being used to whirl that particular object at a constant point O. So from the other formula of angular, that is of the resultant force, which was that is the centripetal force, can be given by mass times the square of the velocity of the body divided by the radius. So from this formula, you can see that the centripetal force is actually inversely proportional to the radius of the path. So centripetal force, if we keep mass and the square of velocity constant, of linear velocity constant, then the centripetal force will be inversely proportional to the radius of the path, which is simply equal to the length of that particular string. Therefore, a shorter string will require a large centripetal force in order for you to keep that particular body rotating in a circular path. So you can actually try this one experimentally. Just take a stone, tie it on a rope, just a small rope or a thread, then start rotating it in a circular path. You will realize that if the length of that particular rope is actually very short, you will require a very large centripetal force within your hand in order to keep that particular stone rotating in that particular circular path. But if the length of the string, or if the length of the rope, or if the radius of the rope or the string is actually large, you will require a very small centripetal force in order for you to keep it rotating in a circular path. So try it experimentally. Just take an object, some heavier object, then tie it on a string, then try rotating it in a circular path. The shorter the path, the more the centripetal force required in your hand for you to keep it rotating in that circular path. And of course, the longer the length of the string, the shorter or the smaller the centripetal force required. Therefore, a shorter string would require a large centripetal force. Therefore, centripetal force is inversely proportional to the radius of the path, or simply is inversely proportional to the length of the string used. Next, let's look at an example which reads that a point on a rim of a wheel has a velocity of 5.6 meters per second. If the rim has a radius of 0.4 meters, calculate part A, the angular velocity of the point. So we are given the velocity, that is the linear velocity v. We are also given the radius. Therefore, we'll simply use a formula for the angular velocity that uses the linear velocity and the radius. Of course, that formula is angular velocity can be given by the linear velocity over the radius. We derived these formulas in our first lesson, so just check. So the linear velocity we are given as 5.6, then divided by the radius is 0.4, of course in SI units. So 5.6 divided by 0.4, you just obtain the angular velocity of 14 radians per second. Then part B, they want us to find the centripetal acceleration. So there are several formulas for finding centripetal acceleration. The first formula is that centripetal acceleration is given by the square of linear velocity over the radius. So because the linear velocity we are given as 5.6, then the radius is 0.4. So 5.6 squared divided by 0.4, you just obtain centripetal acceleration of 78.4 meters per second squared. Similarly, we can also derive other formulas for centripetal acceleration. So from the formula, centripetal acceleration is equals v squared over r. If I separate the values of v, so v squared simply means v multiplied by itself. And we know that v over r, that is simply the formula for the angular velocity. Therefore, if I substitute angular velocity where I have v over r, the formula for centripetal acceleration can as well be, that is the angular velocity multiplied by the velocity, the linear velocity. So acceleration is equals to angular velocity times the linear velocity. Because we already have the angular velocity as 14 radians per second, we'll just multiply with the linear velocity, which was 5.6. So we get the same value of centripetal acceleration as 78.4 meters per second squared. The other way is by deriving another formula for centripetal acceleration. So from the formula v squared over r, I simply want to substitute the value of v. So remember, we said earlier that v, that is we derived actually this particular formula in our previous class. We said that v can be given by omega r, or even from this formula, omega is v over r. So if you make v subject of the formula, you just multiply both sides by r. Therefore, linear velocity is equals to radius times the angular velocity. So if I substitute angular velocity times r where I have v, I'll simply have omega r squared. Of course, if I open this bracket, I'll simply have omega squared over r. Of course, r squared divided by r, I'll just remain with 1r. Therefore, centripetal acceleration can as well be given by angular velocity squared multiplied by the radius. So angular velocity will be, that is centripetal acceleration will be angular velocity squared times the radius. So angular velocity, I already have it as 14 radians per second, then multiplied by the radius, which was 0.4 meters. So this will give me 14 squared multiplied by 0.4, you just obtain 78.4 meters per second squared. So actually, the formula that you use depends with the values provided. So you can see that even if you use the first, the second, or the third formula, the answers will always be the same. Lastly, we look at our second example, which reads that a body having a mass of 0.5 kg is tied to a string and whirled in a horizontal circle of radius 2 meters with a speed of 3.16 meters per second. So calculate part A, the centripetal acceleration. So because we are given the mass of the body, which is 0.5 kg, we are also given the radius r, which is 2 meters, and the linear velocity, which is 3.16 meters per second, or simply the speed. So we'll use the formula for centripetal acceleration that uses at least any two of these particular values provided. So we know that centripetal acceleration can be given by the square of the linear velocity or the speed divided by the radius of the path, which is actually made by that particular body which is being whirled. So we are given the linear velocity or the speed as 3.16 meters per that is 3.16 meters per second. So we'll simply take 3.16 meters per second, then we divide by the radius we are given as 2 meters, so divided by 2 meters. So if you take 3.16 squared divided by 2, you'll simply obtain 4.9928 meters per second squared as our centripetal acceleration. Remember, you can also use other formulas. For example, we have the formula which is involving maybe the radius and other quantities. We have just derived those formulas from our previous slide. So you can check other formulas which are relevant that can help you to find the centripetal acceleration. Then part B, they want us to find the tension in the string. So from Newton's second law of motion, we know that tension is just a force. So the tension is equal to the resultant force. And from Newton's second law of motion, we said that force can be given by ma. So because you already have the value of centripetal acceleration, then we are also given the mass of that particular body, which is 0.5 kg. So I'll simply say that the tension is equal to the resultant external force, which is equal to ma, which is equal to the mass of the body is 0.5 kg times centripetal acceleration. We have just computed it as 4.9928 meters per second squared. Therefore, 0.5 times 4.9928 meters per second squared will simply obtain the tension or the resultant external force being equal to 2.4964 Newton. So lastly, I have an exercise here that I recommend you should try at your own free time to get the understanding of the concepts that you have just learned. Of course, if you have any challenges in handling any of the questions, feel free to drop a comment specifying the question that you need help in, and as usual, I'm always here to try and help where possible. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that good decisions come from experience. Therefore, don't be afraid of experiencing the ups and downs of life. So the quote is encouraging us to be courageous or bold enough in life. We should therefore be open to trying out new experiences in life, because those experiences will help us to learn key lessons that will be essential for our future growth. Remember, the same experience will help you to be a better decision maker in future. And lastly, remember that we become better by overcoming challenges or obstacles. Therefore, unless you try, you will never know how far you could have reached. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you are new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you will get notified. Thank you very much also for 7,000 subscribers. I really appreciate. Until next time, this is Kind Tuition Academy. Thank you very much.